All right, ready to pick up where I left off yesterday on time. So two types of time: calendar or wall clock time and CPU time. And most of this chapter is on calendar time. Regardless of geographic location, Unix systems represent time internally as a measure of seconds since the epoch. That is, since midnight on the morning of January 1st, 1970. Universal Coordinated Time, UTC, previously known as Greenwich Mean Time or GMT. This is approximately the date when the Unix system came into being. Calendar time is stored in a variable or in variables of type time t, an integer type specified by sus_v3. On 32-bit Linux systems, time t, which is a signed integer, can represent dates in the range of the 13th of December 1901 to 19th of January 2038. sus_v3 leaves the meaning of negative time t values unspecified. Wait a minute. Doesn't it have to be negative to go to 1901 since 0 is 1970? Okay, well, thus many current 32-bit Unix systems face a theoretical year 2038 problem, which they may encounter before 2038. If they do calculations based on dates in the future, this problem will be significantly alleviated by the fact that by 2038, probably all Unix systems will have long become 64-bit and beyond. However, beyond, interesting. I haven't seen a 128-bit system before. Let's ask AI. Are there any existing 128-bit consumer CPUs? General purpose registers and address space. 120-bit general purpose CPU would have registers and address buses 120-bit wide and could natively address an enormous memory space of 3.4 times 10 to the 30 bytes. Yeah. Some specialized hardware elements do use 128-bit data paths, but that's not the same as a full 128-bit architecture. SIMD vector registers. Modern CPUs have 128-bit and 256-bit 512-bit vector units via SSE and AVX. They'll let one instruction operate on multiple data elements in parallel, but the core CPU logic address is still 64 bits. Floating point units. Some CPUs support 120-bit floating point operations at IEEE quadruple precision in hardware, but this doesn't make the entire CPU 128-bit. While 128-bit CPUs don't exist in consumer products, memory practical need, 64-bit already supports an enormously or extremely large address space that far exceeds realistic consumer and enterprise needs today. Software systems, operating systems, compilers, drivers, and applications would all need redesigned to benefit. Cost versus benefit. Increasing bit width across the whole system incurs extra hardware complexity without meaningful reward gains for most workloads. Yeah, that's what I was gonna say. All right. 64-bit and beyond. However, 32-bit enabled systems, which typically have much larger lifespan than desktop hardware, may still be afflicted by the problem. Furthermore, the problem will remain for any legacy data and applications that maintain time in 32-bit time t format. The get time of day system, I thought they fixed this. Can we use our QEMU stuff to like CD? There's like if I go under here, what was it called? Something.sh. Chapter 5. Sorry. So we have all this stuff. Can I just temporarily modify this to experiment with the time t? So we got boot VM, create image. Let's do CP star.sh along with the .getignore, the makefile, .clingd. I think that's about it, and put it into chapter 10. CD over to chapter 10. And here, let's say vim makefile. I'm gonna have to patch this thing out. Actually, you know what I'm gonna do? I'm just gonna rm makefile. Or no. Is there anything in here that I actually need for that? I don't think there is. So rm makefile cp chapter 9 makefile into here. Into here, vim makefile. That's what I want to do. Okay, cool. So now if I do get status, I got those scripts and everything, get add all, get status, but don't have any of that stuff. Good. Just run make. There's nothing to be done. Let's do a download ISO, and I want to do it on Alpine. And let's see, let's do create image Alpine, and then install ISO. Oops. Install ISO Alpine. I think I can just do root, right? Something? No, there's no password. So now if I do uname -a, I don't have to install because this thing is already running a, wait a minute, this is i686. Yeah, that's 32-bit Alpine. And if I go back over here, jump to chapter 10 and cat out install, there was i386. Okay. So we're running on 32-bit here. And we want to see what the width of the time t is. Why don't we jump to chapter 10? Let's go ahead and install this. So I have to say setup Alpine. Test, or just localhost, that's fine. That's fine. DHCP is fine. No, that's fine. New password, root. There you go. Don't care, UTC is fine. None. One's fine. No. None. VDA. Sys. Yes. Okay. So now I can just shut down this thing. Reboot or shut down. Okay, I'm gonna say control A C, quit, something like that. Yeah. Okay. And then I'm gonna run boot VM Alpine. Okay. Close out of that. I don't think I need that anymore. Cat boot VM root. There we go. I don't want to mount or update anything, but I do want to install the compiler. So apk update, apk add build base. Maybe I do want a volume mount because I might want to like write a test program. Yeah, let's do that. Oops. So let's volume mount the host here. cd into there, mnt host. Okay. Then in here, I'm just say vim site or time t dot c. Of course, I don't have vim here. Vim time t dot c, and then here I'm gonna say, hey, ChatGPT, write me a basic C program that outputs the size of time t. I mean, I could probably do this pretty quickly myself, but that's what AI is for, right? Main that, do that. There we go. See, it got me there faster. Boom, 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 boom. So just to review what I did, include standard IO and time. Standard IO for printf and time for the size t. Then prints out the size t, returns 0. Great. And because exit success, there we go. And then we just say make, and then we can run build time t, 8 bytes. See, even on a 32-bit system, it's 8 bytes. So I ran this on a 32-bit machine, and it gave 8 bytes as the return. I imagine this is to make software compatible with larger times than the original 32-bit value allowed. Is this a detail of libc or the Linux kernel, or both? So if I go over here, just quit out of this, man up the time t. Oops, yeah, that's good. Time to use time in seconds according to POSIX. Okay, and then there is SU seconds and microseconds. Sign microseconds, okay. History, time, header files, integer type or real floating type. How excessive. In some architectures, the width of time t can't be controlled with the feature test macro time bits. See feature test macro. The following headers also provide time t sketch, sysmessage, select, semaphore, shared memory, stat, time, types, and microtime. The following headers also provide so-and-so. Cool. Good observation, and your intuition is basically right. The short answer is it's primarily a libc ABI decision coordinated with kernel support. Here's how the pieces fit together. Why time t is 8 bytes on 32-bit systems. Historically, 32-bit time t use 32-bit signed integer. This caused the problem. Modern systems have largely fixed this by moving to 64-bit time t even on 32-bit architectures. Who decides size of time t? libc Musil primary decision. Type def defined by libc. Enabling support, the kernel had to change too, but in a different way. Older kernels had syscalls using 32-bit time values. Newer kernels provide parallel time 64 calls. For example, clock, get time. Let's see if can we do man? Do we have man pages here? No. APK add man. Search man, set techo vi, apk search man, man doc, man pages POSIX, man pages, add, there we go, man time t, man, no, those are man pages, search man, man doc, let's try man doc, add man doc, man, hey man, what are we looking for again? I want to look at syscalls on this machine and see if there is a time 64 here. Time 64, no syscall like that, time, no, no time 64, okay. Okay, there's some type of transition. Everyone's on 64-bit now. Great. Cool. Control AC quit. Bam. Oops. Cool. Get add time t. C. Okay, what are we doing now? The get time of day system call returns the calendar time in the buffer pointed to by TV. Okay. Time value, time zone, get time of day, returns the TV argument is appointed to the structure of the following form, time CT, which is in seconds, and then microseconds. If I vim up time t here and I go to the SU seconds t and make that build time t, it's also 8 bytes, man sine microseconds t. Actually what I can do is vim up time and just go to definition. Oops. So many levels of indirection. Okay, comes out to a long int. Great. Although TV microsecond field affords microsecond precision, the accuracy of the value it returns is determined by the architecture-dependent implementation. The U in TV microsecond derives from the resemblance of the Greek letter mu, used in the metric system to denote 1/millionth. On modern x86 32-bit systems, i.e. Pentium systems with a timestamp counter register that is incremented once at each CPU clock cycle, get time of day does provide microsecond accuracy. The TZ argument of get time of day is historical. What's TZ? Okay, that's TZ. Historical artifact in older Unix implementations. It was used to retrieve time zone information for the system. This argument is now obsolete and should always be specified as null. SysV4 marks get time of day obsolete, presumably in favor of POSIX clock API described in section 23.5. Great. Here we go. If the TZ argument is supplied, then it returns a time zone structure whose field contains whatever values were specified in the obsolete TZ argument in the previous call to set time of day. This structure contains two fields, TZ minutes west and TZ DS time. The TZ minutes west field indicates the number of minutes that must be added to the two times in the zone to match UTC, with a negative value indicating that an adjustment to the minutes to the east of UTC, e.g. for Central European time, 1 hour ahead of UTC. This field will contain the value of negative 60. The TZDS time, DST time field contains a constant that was designed to represent the daylight saving time regime in force in this time zone. It is because the DST regime can't be represented using a simple algorithm that the TZ argument is obsolete. This field has never been supported on Linux. So you get time of day manual for further details. The time system call returns the number of seconds since the epoch, i.e. the same value that get time of day returns in the TV sec field of the TV argument. Let's just man syscalls here. Get time of day. Yeah, it's still syscall. And time. I do want to see if there is a time. Saying that there is. There's S time. And there definitely is time. Returns the number of seconds. -1 on error. If the time P argument is not null. Interesting. The number of seconds since the epoch is also placed in the location at which time P points, since time returns the same value in two ways, and the only possible error that can occur when using time is to give an invalid address in the time P argument, fault. We often simply use the following call without error checking. The reason for the existence of two system calls, time and get time of day, with essentially the same purpose is historical. Early Unix implementations provided time. 4.2 BSD added more precise get time of day. System call, the existence of time and a system call as a system call is not redundant. It could be implemented as a library function that calls get time of day. Time conversion functions, figure 10.1 shows the functions used to convert between time T values and the other time formats. Including printable representations. These functions shield us from the complexity brought to such conventions by time zones, daylight saving time, DST regimes, and localization issues. We describe time zones in section 10.3 and locales in section 10.4. SUSV4 marks C time and ASC time obsolete because they do not return localized strings and they're not reentrant. And then we got these kernel, which exposes calendar time, be it time or S time, get time of day, set time of day. What is S time? Let's man up S time. Deprecated. Note this function is deprecated. Use clock set time. S is the set time. You give it the time and it sets it. Okay, this function is deprecated as time sets the system's idea of time and date. The time is pointed to by T. It measures the seconds since the epoch. Executed only by a super user, blah, blah, blah. Okay, so we got this new one, which is called, oh shit, it's today Thursday, damn it. I forgot to put my trash out and I have like garbage in my garage. And the garbage man just went by. Welp. I guess I'm going another week. Yeah, it's fine. Alright, let's see here. I need a better reminder on my calendar for when the freaking trash is coming by. Alright, so we got get time of day, set time of day, time and S time, give you back calendar time, time T, and then, oh, this is all the functions affected as marked star by TZ environment variable plus by locale setting. So these two, locale time and make time, GM time, broken down time as struct TM, user formatted localized string, which is stir F time, stir P time, fixed format string, ASC time, and C time. Okay. Converting time t to printable form, the ctime function provides a simple method of converting a time t value into printable form. Include, what time is it? 1, okay. Include time h, char c time, const time t, time p, returns pointer to statically allocated string terminated by new line and null byte on success or null on error. So this is not reentrant if it's pointing to statically allocated data. Given a pointer to a time t value in time p, ctime returns a 28-byte string containing the date and time in standard format as illustrated in the following example. So this is the ctime. Ctime seems pretty straightforward versus the rest of these. The string includes a terminating null line character and a terminating null byte. The ctime function automatically accounts for local time zone and DST settings. All right. When performing the conversion, we explain how these settings are determined in section 10.3. The return string is statically allocated. Future calls to ctime will override it. SUSV3 states that calls to any of the functions ctime, get, GM time, local time, or ASC time may overwrite the statically allocated structure that is returned by any of the other functions. Oh, so this is like even worse than not reentrant. It's not reentrant with these other functions. In other words, these functions may share single copies of the return character array and TM structure, and this is done in some versions of glibc. If we need to maintain the returned information across multiple calls to these functions, we must save local copies. A reentrant version of ctime is provided in the form of ctime_r. We explained reentrancy in section 21.1.2. This function permits the caller to specify an additional argument that is appointed to a caller supplied buffer that is used to return the time string. Other reentrant versions of functions mentioned in the chapter operate similarly. Convert between time t and broken down to. I don't know why people don't just always use the reentrant version of these library functions. Let's zoom in. ctime. Like, don't you want to have control over how the memory is allocated and the lifetime of it? Like, why would you want to hand that off to glibc and then it mess everything up because it's not managing it right? Okay, convert between time t and broken down time. The GM time and locale time functions convert time t value into so-called broken down time. The broken down time is placed in a statically allocated structure whose address is returned as the function result. So we get this thing back called a TM. Both return a pointer to a statically allocated broken down time structure on success or null on error. The GM time function converts a calendar time into a broken down time corresponding to UTC. The letters GM derived from Brenner's mean time. By contrast, local time takes into account time zone and DST settings to return a broken down time corresponding to the system's local time. So GM time, so local time is kind of like a locale aware version of GM time. Reentrant versions of these functions are provided as GM time R and local time R. The TM structure returned by these functions contains the date and time fields broken into individual parts. The structure has the following form: seconds, minutes, hours, day, month, year, weekday, year day, and is DST. The TM sec field can be up to 60 rather than 59. TM sec field to account for leap seconds. Oh, okay. And are occasionally applied to adjust human calendars to the astronomically exact, the so-called tropical year. If the BSD source feature test macro is defined, then the glibc definition of the TM structure also includes 2 additional fields containing further information about the represented time. The first of these, long int TM GM TOFF, contains the number of seconds that the represented time falls east of UTC. The second field, conch char star TM zone, it's abbreviated time zone name, e.g. CESC for Central European. Summertime +53 doesn't specify either of these fields, and they appear only in a few other Unix implementations, mainly BSD derivatives. The MK time function translates both broken down time expressed in locale time into a expressed as local time expressed into a time t value, which is returned as the function result. The caller supplies the broken down time TM structure pointed to by time pointer. During the translation, the TM W day and TM Y day fields of the TM structure are ignored, obviously, because those aren't really like relevant. A weekday isn't relevant. Why wouldn't year day? I guess you have year. Yeah, you have month here. Day of month. Yeah, all that. So day of week, day of year doesn't really matter. Those are just convenience things. Okay. The MK time function may modify the structure pointed to by time pointer. Obviously, at a minimum, it ensures that TM W day and TM Y day fields are set to values that correspond appropriately to the values of the other input fields. In addition, MK time doesn't require the other fields of the TM structure to be restricted to the ranges described earlier. For each field whose value is out of range, MK time adjusts that field's value so that is in range and makes suitable adjustments to other fields. All these adjustments are performed before MK time updates the TM weekday and TM year day fields and calculates the return time t value. For example, if the input TM sec field were 123, then on return the value of this field would be 3, because it would mod the value, and the value of the TM min field would have 2 added to whatever value it previously had, and if that addition caused TM min to overflow, then the TM min value would be adjusted, and the TM hour field would be incremented, and so on. These adjustments even apply for negative field values. For example, specifying -1 for TM sec means the 59th second of the previous minute. This feature is useful since it allows us to perform date and time and arithmetic on a broken down time value. The time zone setting is used by MK time when reporting the translation. In addition, the DST setting may or may not be used depending on the value of the input TSIS DST field. If TMIS is DST is 0, treat the time as standard time, ignore DST even if it would be in effect at this time of year. If TM is DST is greater than 0, treat this time as DST, i.e. behave as though DST is in effect, even if it would not normally be so at this time of year. If TM is DST is less than 0, attempt to determine if DST would be in effect at this time of year. This is typically the setting that we want. On completion, and regardless of the initial setting of is the DST, make time sets the is DST field to a positive value if DST is in effect at the given date, or to 0 if DST is not in effect. Bam. Converting between broken down time and printable form. In this section, we describe functions that convert broken down time into printable form and vice versa, converting from broken down time to printable form. Given a pointer to a broken down time structure in argument TM ASC time, returns a pointer to a statically allocated string containing the time in the same form as CS time. C time, sorry. ASC time. By contrast with C time, local times, let's go back to this diagram here. Okay, so ASC time just takes the broken down structure, converts it to printable. By contrast with C time, local time settings have no effect on ASC time since it is converting a broken down time, which is typically either already localized via local time or in UTC as returned by GM time. As with C time, we have no control over the format of the string produced by ASC time. A reentrant version of ASC time is provided by blah, blah. Listing 10.1 demonstrates the use of ASC time as well as all of the time conversion functions described so far in this chapter. Okay. This program retrieves the current calendar time and then uses various time conversion functions and displays the results. Here's an example of what we see when running the program in Munich, Germany, which in winter is on Central European time, 1 hour ahead of UTC. Okay, let's go ahead and get this source from the website, which is here. It's called, what, calendar time C? Yep. Let's grab that. Copy link address, mkdrp, ref. This is under time. CD under there, W get that, bam. Let's go back over to here and make. Sorry, I went back here. Make. There we go. So I also need to go under ref lib, mkdr lib, and we're rsync AV. Let's go back to program interface. Find type D name lib. So rsync avzci chapter 9 ref lib into chapter 10 ref lib. Bam. Cool. CD chapter 10 make build ref time calendar time. Bam. Date. So January 8th 2026, second since epoch, about 56 years. Wow. So we got get time of day, gave us back the seconds, but also microseconds, broken down by GMT and broken down by local time. So the hours adjusted because we're 7 hours off from GMT. Everything else is the same. ASC time formats the GMT value as, so we're technically right now 13. Yeah. C time, make time. Okay, so when they convert a make time of the GM time, then that comes back higher than the local time. Makes sense. And the date, of course, is the right thing. None of these print like the time zone, like the what you normally expect from date. Cool. It all makes sense. Nothing surprising. Okay, the stir f time function provides us with more precise control when converting a broken down time into printable form. Given a broken down time pointed to by time PTR, stir f time places a corresponding null terminated date plus time string in the buffer pointed to by outstir. Okay. These are not part of the syscall interface. It's just libc stuff. The string returned in outstir is formatted according to the specification in format. The max size argument specifies the maximum space available to outstir. Unlike ctime, And ASC time, stirf time doesn't include a new line character at the end of the string unless one is included in the format. On success, stirf time returns the number of bytes placed in outstir, excluding the terminating null byte. If the total length of the resulting string, including the terminating null byte, would exceed max size, then stirf time returns 0, indicating an error, and the contents of outstir are indeterminate. The format argument of stirf time is a string akin to that given to printf, which are replaced by printf sequences beginning with the percent character. Percent are conversion specifications, which are replaced by various components of the date and time according to the specifier character following the percent character. A rich set of conversion specifiers is provided, a subset of which is listed in table 10.1. For a complete list, see stirf time 3 manual page. Except as otherwise noted, all of the conversion specifiers are standardized in susv3. The %cap_u and %cap_w specifiers both produce a week number in the year. The cap_u week numbers are calculated such that the first week containing a Sunday is numbered 1. And the partial week preceding that is numbered 0. If Sunday happens to fall as the first day of the year, then there's no week 0. As the last day of the year falls in week 53, the %w week number work the same way, but with Monday rather than Sunday. Often we want to display the current time in various demonstration programs. In this book, for this purpose, we provide the function cur_time, which returns a string containing the current time as formatted by stirf time when given the argument format. This is a library function that he wrote. The current time function implemented should blah blah. Okay, select the conversion specifiers. Function that returns a string. So let's just read this. Return a string concatenating this current time formatted according to the specification of format. See stirf times. First specifiers in format is null. We use %c as a specifier, which gives the date and time as c time. Time as for c time. But without the trailing new line, returns null and error. We go down here. Char targ, yeah, this is the library function he has. So you give it the format string. It then allocates a time t, a size t, s, a struct for the broken down time, and a character buffer that's static, making this non-reentrant. And then we call time, which is of course deprecated. If we do man to time, it's going to be like, hey, it's deprecated. Oh no, it's not deprecated. Or it's redundant according to get time of day. Get time of day. There we go. So this one's deprecated. Interesting. Okay. So we call time on null, which is back to current time. We then convert that to a local time with local time. Reference that. If it's null, then return null. And then we have stirf time. We give the buffer's buff size, which is not defined in this code snippet. And then we say, hey, if format's not equal to null, then we give the format, also give it a %c. And referencing up here, %c is a date and time, just the convenient shorthand there. Then we return the s. If s is equal to 0, then return null because there's an error, or return buffer. So all this is non-reentrant. Great. I guess the benefit of like non-reentrant statically allocated memory is that it doesn't need to be garbage collected later. You don't have to free it. But the downside is that you can't concurrently call this thing because it's going to be concurrently writing the same bits of memory. So I can see why they created these non-reentrant versions. But I'd rather have full control over it and just use the reentrant version. Converting from printable form to broken down time. The stir p time function is the converse of stir f time. It converts a date plus time string in broken down time. It converts a date plus time string to a broken down time. So just the inverse. The stir p time function uses the specification given in format to parse the date plus time string given in stir and places the converted broken down time in the structure pointed to by time ptr. On success, stir p time returns a pointer to the next unprocessed character in stir. This is useful if the string contains further information to be processed by the calling program. If the complete format string could not be matched, stir p time returns null to indicate the error. The format specification given to stir p time is akin to that given of scanf. It contains the following types of characters. Conversion specifications begin with the % character, whitespace characters, which match 0 or more white spaces in the input string, and non-whitespace characters other than %, which must match exactly the same characters in the input string. Okay. Okay. The conversion specifications are similar to those given to stirf time. The major difference is that the specifiers are more general. For example, both %A and %kappa can accept a weekday name in either full or abbreviated form, and %D or %E can be used to read the day of the month with or without deleting 0. In the case of single digit days, in addition, cases ignored, for example, May and May are equivalent month names. The string %% is used to match the % character in the input string. The stir p time 3 manual page provides more details. The glibc implementation of stir p time doesn't modify those fields in the TM structure that are not initialized by specifiers in the format. This means that we can employ a series of stir p time calls to construct a single TM structure from information in multiple strings, such as a date string and a time string. While SSV3 permits this behavior, it doesn't require it, and so we can't rely on it on other Unix implementations. In a portable application, we must ensure that stir and format contain input that will set all fields of the resulting TM structure, or make sure that the TM structure is suitably initialized before calling stir p time. In most cases, it would be sufficient to zero out the entire structure using memset, but be aware that the value of 0 in the TMMday field corresponds to the last day of the previous month in the glibc. In many other implementations of the time conversion function, finally note that stir p time never gets set. The value of the TM is the SC field of the TM structure. The GNU-C library also provides two other functions that serve a similar purpose to stir p time: get date, specified in SSV3 and widely available, and is reentrant analog get date _r, not specified in SSV3 and available only in a few other Unix implementations. We don't describe these functions here because they employ an external file identified by an environment variable date mask to specify the format used for scanning the date, which makes them somewhat awkward to use and also creates security vulnerabilities in set user ID programs. Okay. Listing 10.3 demonstrates the use of stir p time and stir f time. This program takes a command line argument containing the date and time, converts. Hold on. 10.3. Alright. This program takes a command line argument containing a date and time, converts this to broken down time using stir p time, and then displays the result of performing these reverse conversions to stir f time. The program takes up to 3 arguments, of which the first 2 are required. The first argument is the string containing the date and time. The second argument is the format specification to be used by stir p time. To parse the first argument, the optional third argument is the format string to be used by stir f time. For the reverse conversion, is an argument is omitted. The default format string is being used. We describe set locales function used in this program, section 10.4. The following shell session logs show some examples of the use of this program. Stir time, you give it the thing, parses it out, great. The following usage is similar, but this time we explicitly specify a format for stir f time. Great. I'm not gonna mess with that. Time zones. Boop. Different countries and sometimes even different regions within a single country operate on different time zones and DST regimes. Programs that input and output times must take into account the time zone and DST regime of the system on which they run. Fortunately, all these details are handled by the C library. Doubtful, given that different countries change their DST algorithm like randomly. So I doubt libc handles everything. Time zone definitions. Time zone information tends to be both voluminous and volatile. For this reason, rather than encoding it directly into programs or libraries, the system maintains this information in files in standard formats. Oh, okay. That's how they keep everything up to date. These files reside in a directory user share TZ info. I'm going to poke around a little bit and see what my TZ info file has in it. User share TZ info. Or zone info, sorry. What? It's a directory, okay. Bunch of binary stuff. Okay. Well, I want to do America, Denver, MST and MDT. Fascinating. TZIF. I want to see what. Okay. If we do, go away. Quit all. File. America, Denver. It's a time zone data FAT. Version 2. 6 GMT time flags, standard flags, no leap second. Interesting. Alright, let's continue reading. Each file in this directory contains information about the time zone regime in a particular country or region. These files are named according to the time zone they describe. So we may find files with names such as EST, US Eastern Standard Time, CET, Central European Time, UTC, Turkey, and Iran. In addition, subdirectories can be used to hierarchically group related time zones. Under a directory such as Pacific, we may find the files Auckland, Port Moresby, and Galapagos. When we specify a time zone for use by a program in effect, we are specifying a relative path name for one of the time zone files in this directory. The local time for the system is defined by the time zone file etc local time. Cat out etc local time. That's another weird file. Oh, it's just a symlink. So it says the local time for the wait a minute. The local time for the system is defined by the time zone file etc local time, which is often linked to one of the files in user share zone info. The format of time zone files is documented in the TZ file manual page. Time zone files are built using ZIC, a zone information compiler. Is that even on here? What? It's amazing what comes with all these. Time zone compiler, interesting. The zdump command can be used to display the time as it would be currently according to the time zone in specified time zone file. Zdump man. Let's see, zdump for etc local time. And what if I do like user share America? Sorry, time zone info America star. We would have to grab everything, and so we have to say find in that directory type D, or not type D, type F. And then, oops, xarg zdump. Look at that. There's a lot of time zones in America. North Dakota has 3 time zones? They're all the same. Why do they need 3 names? Kentucky, what are you doing here? Probably people just want to put their own city name. Indiana. These actually are different. Alright. Cool. To specify a time zone when running a program, we set this TZ environment variable to a string. Oops, I'm on the wrong page here. Boop. To a string consisting of a colon followed by one of the time zone names defined in user share zone info. Setting the time zone automatically influences the function ctime, local time, make time, and stirf time. To obtain the current time zone setting, each of these functions uses tzset, which initializes 3 global variables. I wanted to go back and look at this diagram of all the library. So none of the kernel stuff is the get time of day and the time function, the syscall, get time of day and time syscalls are not time zone aware or locale aware. Let's go over here and say, on Linux, what is the difference between time zone aware functions and locale aware? Time zone awareness is about interpreting or converting absolute time. It's questions like, let's go down locale. How should this be presented to humans? Oh, okay. That's like the formatting. That makes sense. Cool. All right. So the thing that I just wanted to reiterate is that both the syscall time and the syscall get time of day provided by the kernel have no concept of locale or time zone. They're just incrementing counters. And then all that other stuff is layered on top of those syscalls by libc. All right. To obtain the current time zone, we set time zone setting. Each of these functions uses tzset3, which initializes 3 global variables. Char, tz name of the time zone, and alternate DST time zone. Int daylight, non-zero if there is an alternate DST time zone. Long time zone, seconds difference between UTC and local standard time. Wow, it's down to the seconds. Okay. The tzset function first checks the tz environment variable. So this is all in environment variables and global variables. If this variable is not set, then the time zone is initialized to the default defined in the time zone file etc local time. If the tz environment variable is defined with a value that can't be matched to a time zone file, or it's an empty string, then UTC is used. The tz, so if I can run like something like date, or I can run tz is equal to some garbage date, and that'll put me back to UTC. Yeah. Or I could say like America, New York. Or I could say like America, LA, Los Angeles. Yeah. Cool. We can see the effect of TZ variable running the program listed in 10.4. In the first run, we see the output corresponding to the system's default time zone, Central European time. In the second, we specify a time zone for New Zealand, which at this time of year is on daylight saving time, 12 hours ahead of CET. Cool. Oh, and I didn't have to specify the colon. Interesting. All right, next page. Boop. SUSV3 defines two general ways in which the TZ environment variable can be set. As just described, TZ can be set to a character sequence consisting of a colon plus a string that identifies the time zone in an implementation-specific manner, typically as a path name, for a time zone description file. Linux and some other Unix implementations permit the colon to be omitted, which is what I did when using this form, but SUSV3 doesn't specify this. For portability, we should always include the colon. The other method of setting TZ is fully specified in SUSV3. In this method, we assign a string of the following form to TZ. Boom. Standard. Oh, come on, man. Standard offset, DST offset, start date / time, end date / time. Spaces are included in listing above for clarity, but none should appear in the TZ value. The brackets are used to indicate optional components. This SCD and DST components are strings that define names for the standard and DST time zones, for example, CST and CEST. For Central European time and Central European summer time, the offset of each case specifies the positive or negative adjustment to add to the local time to convert it to UTC. The final four components provide a rule describing when the change from standard time to DST occurs. The dates can be specified in a variety of forms, one of which is month. I don't know what that is. This notation means day D of week N of month M. If time is omitted, it defaults to 2 a.m. in each case. Here's how we could define TZ for Central Europe, where standard time is 1 hour ahead of UTC, and DST running from the last Sunday in March to the last Sunday in October is 2 hours ahead of UTC. I don't really care for that. We omitted the specification of time for the DST changeover since it occurs at the default of 2 a.m. Of course, the preceding form is less readable than a near equivalent to Europe Berlin. Locales. Several thousand languages spoken across the world, of which a significant percentage are regularly used on computer systems. Furthermore, different countries use different conventions for displaying information such as numbers, currency, amounts, dates, and times. For example, in most European countries, a comma rather than a decimal point is used to separate the integer and fractional parts, real numbers, and of real numbers. And most countries use formats for writing dates that are different from the month, day, year format used in the United States. SUSV3 defines a locale as a subset of the user's environment that depends on language and cultural conventions. Ideally, all programs designed to run in more than one location should deal with locales in order to display and input information in the user's preferred language and format. This constitutes the complex subject of internationalization. In the ideal world, we would write a program once, and then whenever it is run, it would automatically do the right thing when performing I/O. That is, it would perform the task of localization. Internationalizing programs is a somewhat time-consuming job, although various tools are available to ease the task. Program libraries such as GLPI also provide facilities to help with the internationalization. The term internationalization is often written as I-18N for I plus 18 letters plus N, as well as be quicker to write. This term has the advantage of avoiding the difference in the spelling of the term itself in British and American English. Let's go over here and say, hey AI, what is the difference between internationalization and localization? They're distinct concepts. It's easy to remember the difference. Internationalization prepares software for the world. Localization adapts it to a specific place. Okay. Cool. Okay. Locale definitions, like time zone information, locale information tends to be both voluminous and volatile. For this reason, rather than requiring each program and library to store locale information, the system maintains its information files in standard formats. Boom. Locale information is maintained in a directory hierarchy under users share locale in some distributions. So let's look under there. CD user share locale. Locale. LT. So if you go under EN, oops. All right, so if we go under EN US, and then just run LT under here. What's this? KF desktop entry? US English. I don't know what the rest of this stuff is. Is this how you say English in those languages? Yeah. So in Finnish, it's American Englanti. Ingles de EU. And then there's these LC messages. The hell is this shit? LC messages, G settings, MO. It looks like a binary file of some sort, but with a lot of text. Let's do a file on this. GNU message catalog, little endian. GitLab gnome org. These look like headers, like HTTP headers. It's a 12H. Okay. Let's move on. Locale information is maintained under there. Each subdirectory under this directory contains information about a particular locale. These directories are named using the following convention: language _ territory .codeset @ modifier. The language is a 2-letter ISO language code, and the territory is a 2-letter ISO country code. The code set designates a character code encoding set, and the modifier provides a means of distinguishing multiple locale directories whose language, territory, and code set are the same. An example of a complete locale directory name is de_de.utf@euro. As the locale for German language, Germany, UTF character encoding employing the euro as a monetary unit. As indicated in the brackets shown in directory naming format, various points of the name of the locale directory can be omitted. Often the name consists of just a language in a territory. Thus, the directory ENUS is the locale directory for the English-speaking United States, or FRCH is the locale directory for the French-speaking region of Switzerland. The CH stands for Confederatio Helvetica, and the Latin and thus locally language neutral name for Switzerland. With 4 official national languages, Switzerland has an example of a locale analog for a country with multiple time zones. When we specify a locale to be used within a program, we are in effect specifying the name of one of the subdirectories under user share locale. If the locale specified in the program doesn't match the locale directory name exactly, then the C library searches for a match by stripping components of the specified locale in the following order: code set, normalized code set, territory modifier. The normalized code set is a version of the code set name in which all non-alphanumeric characters are removed, all letters are converted to lowercase, and the resulting string is prepended with the character's ISO. The aim of normalizing is to handle variations in the capitalization and punctuation, e.g. extra hyphens of code set names. As an example of stripping process, if a locale for a program is specified as frch.utf8, but no locale directory or that name exists, then the frch locale directory will be matched if it exists. If the frch directory doesn't exist, then the fr locale directory will be used. In the unlikely event the fr directory doesn't exist, then the set locale function described shortly will report an error. The file user share locale alias is defined. Alternative ways to specify locale to a program. See the locale aliases 5, manual page for details, don't care about that. Boop. It's a lot of niche time zone internationalization stuff. Under each locale subdirectory is a standard set of files that specify conventions for this locale, as shown in table 10.2. Note the following further points concerning the information of this table. The LC collet, I don't have that, in US file defines a set of rules describing how the characters in a character set are ordered, i.e. alphabetical order for a character set. These rules determine the operation of stir col and stir xfrm, 3 functions. Even languages using Latin-based scripts don't allow the same ordering rules. For example, several European languages have additional letters that, in some cases, sort after the letter Z. Other special cases include the Spanish 2-letter sequence LL, which sorts to a single letter after L, and the German umlauted characters such as A umlaut, which corresponds to AE and sorts as those 2 letters. The LC messages directory is one step towards internationalizing the messages displayed by a program. More extensive internationalization of program messages can be accomplished through the use of either message catalogs, see the Catopen 3 and catgets 3 manual pages, or the GNU Get Text API available at GNU. Okay. Okay. Version 222 of glibc introduced a number of new non-standard locale categories. The LC address defines rules for locale-specific representations of a postal address. LC identification defines information identifying the locale. LC measurement defines the measurement system of the locale, e.g. metric versus imperial. LC name defines the locale-specific rules for representation of a person's name and title. LC paper defines the standard paper size for the locale, e.g. US letters versus A format paper used in most other countries. LC telephone defines the rules for locale-specific representation of domestic and international telephone numbers, as well as international country prefixes and international dial-out prefix. Contents of locale-specific subdirectories. LCC type file containing character classifications is alpha and rules for case conversions. LC collet file containing the collation rules for character set. LC monetary file containing formatting rules for monetary values. C locale conv and locale.h. LC numeric, a file containing formatting rules for numbers other than monetary values. C locale conv and locale.h. LC time, file containing formatting rules for dates and time. LC messages, a directory containing files specifying formats and values used for affirmative and negative yes and no responses. The actual locales that are defined on the system can vary. SUSV3 doesn't make any requirements about this except that the standard locale name POSIX is synonymously C and synonymously C, a name that exists for historical reasons, must be defined. This locale mirrors the historical behavior of Unix systems, thus it is based on an ASCII character set and uses English for names of days and months and for yes-no responses. The monetary and numeric components of this locale are undefined. The locale command displays information about current locale environment. Within the shell, the command locale-a lists the full set of locales defined on the system. Locale, didn't even know that was a thing. Yeah, it just says, hey, everything's ENUS UTF-8. Cool. Specifying the locale for a program. Okay. And then we get into updating the system clock, the software clock, jiffies, process time, which is what I'm more interested in, and all this calendar time crap. Example, program, and then summary. Am I gonna get through this? Yeah, okay. Specifying the locale of a program. The set locale function is used to both set and query a program's current locale. So you say, hey, give me back a char star. I'm going to call it set locale. Here's the category, and here's a const char to the locale. Returns a pointer to a usually statically allocated string identifying the new or current locale in success or null in error. The category argument selects which part of the locale to set or query, and this is specified as one of the set of constants whose names are the same as the locale categories listed in table 10.2. Okay. Thus, for example, it is possible to set the locale for time displayed to be Germany while setting the locale for monetary display to be US dollars. Interesting. Alternatively, and more commonly, we can use the value lc_all to specify that we want to set all aspects of the locale. There are two different methods of setting the locale using set locale. The locale argument may be a string specifying one of the locales defined in the system, i.e. the name of one of the subdirectories under the user lib locale, such as DEDE or ENUS. Alternatively, locale may be specified as an empty string, meaning the locale setting should be taken from environment variables set locale lc_all empty string. We must make this call in order for a program to be cognizant of the locale environment variables. If the call is omitted, these environment variables will have no effect on the program. When running a program that makes a set locale lc_all empty string call, we can control various aspects of the locale using a set of environment variables whose names again correspond to the categories listed in temp 2. Alternatively, we can use the lc_all or the lang environment variable to specify the setting of the entire locale. If more than one of the preceding variables is set, then lc_all has precedence over all of the other lc environment variables. The lang has lowest precedence, thus it is possible to use lang to set a default locale for all categories, and then use the individual lc* variables to set aspects of the locale to something other than this default. As a result, set locale returns a pointer to usually statically allocated string that identifies the locale setting for this category. If we are interested only in discovering the current locale setting without changing it, then we can specify the locale argument as null. Locale settings control the operation of a wide range of GNU Linux utilities, as well as many functions in glibc. Among these are functions stir, ftime, and stir ptime, as shown by the results of stir ftime when we run the program in listing 10.4 in a number of different locales. Say, hey, show time, DE, LC time. Okay. Updating the system clock. We now look at two interfaces that update the system clock, set time of day, and adjust time. Which, if we go back to our little diagram, which was way back at the beginning of the chapter, it has S time instead of adjust time. So let's run man2 on ADJ time. Maybe as man3. Okay. These interfaces are rarely used by application programs since the system time is usually maintained by tools such as Network Time Protocol daemon, and they require the call to be privileged, capsys time. The set time of day system call performs the converse of get time of day, which we described in section 10.1. It sets the system's calendar time to the number of seconds and microseconds specified in time value structure pointed to by TV. Set time of day, blah, blah, blah. As with get time of day, the use of TZ argument is obsolete, and this argument should always be specified as null. The microsecond precision of the TV microsecond field doesn't mean that we have microsecond accuracy in controlling the system clock, since the clock's granularity may be larger than 1 microsecond. Although set time of day is not specified in SUSV 3, it is widely available on other Unix implementations. Linux also provides the S-time system call for setting the system clock. The difference between set time of day and S-time is that the latter call allows the new calendar time to be expressed with a precision of only 1 second. As with time and get time of day, the reason for the existence of both S-time and set time of day is historical. The latter, more precise call was added by 4.2 BSD. Why does it say that they're deprecated if they have more precision? See, deprecated. Let's see. Let's ask AI. My man pages on Linux say set time of day syscall is deprecated. Why? What should I use otherwise? And then let's do man to S time. It's also deprecated. Clock set time recommended. Man, clock. Some guy walking up my driveway right now. I hate that people can just walk into my fucking yard. What is this guy's problem? I'll be right back. All right. That was a really nice gentleman with the gas company wanting to inspect my gas lines to make sure there's no leaks. Okay, where do we leave off here? Updating stuff. So now we rely on these clock set times. Functions. Syscalls here. No, that is a library function. Is there a 2 version of this? Yeah. Get res, get time, set time. What is get res? What does res mean? Resolution? How do you get a clock ID though? Man syscalls clock underscore. So you got nano sleep, wow, a lot of stuff. Set time, get res, adjust time. I think ADJ time is adjust time. Linux uses David L. Mills clock adjustment algorithm. RFC 5905. That's got to be pretty cool to be like permanently in technology history. And in the man page is David L. Mills. Let's see. RFC 5905. Network time protocol. This person must have worked extensively on network time protocol stuff. Let's see here. Cool. All right. Suffice to say, there's been changes to a lot of this stuff. Okay. Set time of day system call performs converse of get time of day. It is set to system counter time to number of seconds since a microsecond specified in time value structure pointed to by TV. As with get time of day, the use of the TZ argument is obsolete, and this argument should always be specified as null. Microseconds precision of TV and microsecond field doesn't mean that we have microsecond accuracy. I thought I already read this. Yeah, I already read this. I'm over here. Abrupt changes to the system time of the sort caused by calls to set time of day can have deleterious effects on applications, e.g. make a database system using timestamps or timestamp log files that depend on a monotonically increasing system clock. For this reason, when making small changes to the time of the order of a few seconds, it's usually preferable to use the adjust time library functions, which cause the system clock to gradually adjust to the desired value. Adjust time. The delta argument points to a time val structure that specifies the number of seconds and microseconds by which the change the time. If the value is positive, then the small amount of additional time is added to the system clock each second until the desired amount of time has been added. If the delta value is negative, the clock is slowed down in a similar fashion. The rate of clock adjustment on Linux x86-32 amounts to 1 second per 2,000 seconds, or 43.2 seconds per day. It may be that an incomplete clock adjustment was in progress at the time of the adjust time call. In this case, the amount of remaining unadjusted time is returned in the time value structure pointed to by old delta. If we are not interested in this value, we can specify old delta as null. Conversely, if we are interested only in knowing the current outstanding time correction to be made and don't want to change the value, we can specify the delta argument as null. Although not specified in SysV3, adjust time is available on most Unix implementations. On Linux, adjust time is implemented on top of a more general and complex Linux-specific system call called adjust time X. This system call is employed by the network time protocol daemon. For further information, refer to the Linux source code, the Linux adjust time X2 manual page, and the NTP specification. Mills, 1992. He's in the book too. This Mills guy gets around. Looks like he did a lot of work on NTP. The software clock jiffies. The accuracy of various. I'm gonna pull up this guy. Was it David Mills? Let's see, David L. Mills. Oh, he passed away a couple years ago. That's sad. He didn't look too old. He's 85. David Mills is an American computer engineer and professor emeritus at the University of Delaware. He was an internet pioneer who led the Gateway Algorithms and Data Structures Task Force. Gateway Algorithms and Data Structures. What is that? Was the precursor to the IETF. I've never even heard of this. This is so it predated. It was the precursor to the IETF. Wow, this guy was an OG. How have I not heard of him? In January 1986, a year after I was born, the Internet Activities Board, now called the Internet Architecture Board, decided to divide GADS into two entities: the Internet Architecture Task Force, chaired by Bills, to pursue research goals, and the IETF to handle near-term engineering technology transfer issues. First IETF chair was Mike Corrigan, who was then the technical program manager for the Defense Data Network, DDN. Also in 1986, after leaving DARPA, Robert E. Kahn founded the Corporation for National Research and CNRI, which began providing administrative support to the IETF. Wow. It's got to be in the IETF Wikipedia page. Okay. He was known as the Internet's Father Time for designing the network time protocol, which is intended to synchronize all participating computers across different computer systems and networks to within a few milliseconds of coordinated universal time. Early life and education. David Lennox Mills was born. I don't really care. I don't really care about his personal life. I guess career. IEEE, IETF, GEDS, University of Delaware, NTP, ARPANET. In 1977, Mills began work at ComSat on synchronizing the clocks of computers connected to ARPANET, inventing the network time protocol. I didn't realize NTP was that old. NTP is intended to synchronize all participating computers to within a few milliseconds of coordinated universal time, UTC. He told The New Yorker in 2022, just a few years ago, that he enjoyed working on synchronous time because no one else was working on it, giving him his own little fiefdom. In the mid-2000s, Mills turned over full control of NTP reference implementation to Harlan-Stein. Mills was a contributor to the standards and software that came to be the internet. He was the chairman of the Gateway Algorithms Data Structure Task Force and the first chairman of the Internet Architecture Task Force. He invented the DEC LSI 11-based fuzzball router that was used for the 56 kilobit NSFnet 1985. He inspired the author of Ping. This guy is like so OG. I can't believe I haven't heard of him. He authored 28 RFCs. Wow, I guess I haven't been reading enough RFCs, including 2 internet standards. In 1999, he was inducted as a fellow of the Association for Computer Machinery, and in 2002, he was inducted as a fellow of the Institute of Electrical and Electronic Engineers for contributions to network protocols and network timekeeping and the development of the internet. In 2008, Mills was elected a member of the National Academy of Engineering, NAE, for contributions to internet timekeeping and the development of the network time protocol. In 2013, he received the IEEE Internet Award for significant leadership and sustained contributions in the research, development, standardization, and deployment of quality time synchronization capabilities for the internet. Mills was a professor emeritus at the University of Delaware, where he was a full professor from 1986 to 2008. He subsequently held an adjunct appointment at Delaware so that he could continue to teach. Adjunct appointment. His vision began worsening around 2012, and by 2022 he was fully... Oh, so sad. Mills died in New York, Delaware, January 17th, 2024. At age 85, Mills' wife died later. Okay. So sad. Okay. Let's look for where the man pages are located. I could do like strace, right? strace man 2. Do Pac-Man trace. Sorry, S trace. I think I can just do this. Yeah. Let's do. Now if I run this, oop. Let's just grab for man. Yeah, I'll just ask AI. Actually, give me 1 second here. Un momento, por favor. Alright, I want to just view the open syscalls. So man strace. Look for open. Open. Using strace, how do I just trace open syscalls? So we can say strace dash e trace is equal to open dot comma open at. Get rid of the grep and follow execs. Gotta get the open at 2. Okay. Oh, and I need to pipe dev null. Clear. Dev null and 2 and 1. No. I need that for all the syscalls. Alright. Clear. Alright. So all these are paths. User share man. Oh, these are GZ'd. Ah, bummer. Oh well, I'm not gonna bother with it. Anyways, we can close out of this, close out of that, go back over here. All right, time is it? I got 30 minutes to before I have to wrap things up here. So we were on the software clock, jiffies. The accuracy of various time-related system calls described in this book is limited to the resolution of the system software clock. Which measures time in units called jiffies. The size of a jiffy is defined by the constant hz within the kernel source code. This is the unit in which the kernel allocates the CPU to process under the round-robin time-sharing scheduling algorithm. Oh, this is software clock. This is not. We're beyond wall clock stuff now, right? Yeah. On Linux x86-32 and kernel versions up to and including 2.4, the rate of the software clock was 100 hertz. That is, a jiffy is 10 milliseconds. Because CPU speeds have greatly increased since Linux was first implemented, in kernel 260 the rate of the software clock was raised to 100 hertz. On Linux x86-32, the advantage of a higher software clock rate are that timers can operate with greater accuracy and time measurements can be made with greater precision. However, it isn't desirable to set the clock rate to arbitrary high values because each clock interrupt consumes a small amount of CPU time, which is time that the CPU can't spend executing processes. Debate among kernel developers eventually resulted in the software clock rate becoming a configurable kernel option under processor type and features timer frequency. Since kernel 2613, the clock rate can be set to 100, 250, the default, or 1000 hertz, giving Jiffy values of 10, 4, and 1 millisecond, respectively. Since kernel 2620, a further frequency is available, 300 hertz, a number that divides evenly for two common video frame rates, 25 frames per second PAL and 30 frames per second NTSC. Process time. Process time is the amount of CPU time used by a process since it. So what was this Jiffy stuff? I don't understand that. And this, I'm gonna ask AI. Can you elaborate on what Jiffies, Jiffies, are in Linux and why they are named that? Jiffy's core Linux kernel timekeeping concept and the name of some history behind it has some history behind it. What are Jiffies? Linux Jiffies is a global kernel counter that represents a number of timer interrupts, ticks. So these are timer interrupts that have occurred since the system booted. Jiffies is tick since boot. Each tick corresponds to one interrupt generated by a hardware timer at a fixed frequency called HD. The role of HD. HD is a compile time kernel constant that defines how many timer interrupts happen per second. Timer interrupts happen per second. That makes sense. What is Jiffies used for? Jiffies is a kernel's basic unit of time measurement for many internal operations, scheduling time slices, timeouts, and delays. So this is how it does rescheduling then. So does that mean that like when this happens, some kernel code runs? Timeout and delays, expiring timers, counting CPU timers, polls, select timeouts, network time. It is monotonic, never goes backwards, and wraps around after overflowing. Handle carefully. High-resolution timers and tickless kernels. Modern kernels complicate the story slightly. High-resolution timers, HR timers, allow timers with precision better than a Jiffy. No hertz, tickless kernels stop periodic ticks when CPUs are idle. Despite this, Jiffies still exist. It still advances logically. The kernel synthesizes missing ticks when CPUs wake up, so Jiffies remain a logical time base, not strictly one interrupt per jiffy anymore. Why are they called jiffies? The name predates Linux and comes from older computing and engineering slang. Historically, jiffy meant a very short, imprecise interval of time. I'll be there in a jiffy. These guys. In electronics and early... actually, give me 1 second. In electronics and early operating systems, a jiffy often meant 1 clock tick, the shortest time interval the system code can conveniently measure. Examples: IBM mainframe documentation, DEC systems, early Unix discussions. Linux inherited a term to mean the smallest unit of time measured by the kernel timer. It's intentionally informal, reflecting that it's not a physical second, just a kernel-defined tick. Mental model summary: think of jiffies as a monotonic increasing tick counter used by the kernel as a coarse-grained notion of time. It's not very high in its resolution. Scope: kernel internal timing. If you want, I can walk you through exact code path where jiffies is incremented, show how timeouts uses jiffies. Compare jiffies to k time t. Should not use jiffies, just say the word. Okay, if we scroll up here, how do timer interrupts work in this situation? Say I have a heavy CPU workload running in user space on all cores of the system, doing no syscalls, just math, completely CPU bound. Would these timers that increment jiffies interrupt the user space process and then resume it? Linux relies on a hardware interrupt timer, especially the programmable interval timer, PIT, or APIC timers on modern CPUs. To keep track of time and schedule processes, the timer is programmed to fire periodically at Hertz frequency. When the timer fires, the CPU receives an interrupt. No matter what it is doing, the CPU pauses whatever it's doing, switches to kernel mode, executes the interrupt handler, and then returns to whatever it was doing, user space kernel. So even if your CPU is fully busy in a tight user space loop doing math, the CPU executes the math instructions, a timer interrupt occurs, the CPU pauses the math code, jumps to the kernel interrupt handler, the interrupt handler increments jiffies and performs any other timer work, e.g. updating schedulers, timers. The kernel returns to the user space math code, resuming exactly where it left off. Context switches and preemption. The timer interrupt also drives the scheduler. Each CPU has a time slice for the current remaining running task. When the timer interrupt fires, the kernel checks if the running task has executed its time slice. If so, it sets a flag so that the scheduler picks a new task to run. This can cause a context switch. Your CPU-bound process may be paused and another process scheduled. After the scheduler runs, your process may resume later, either on the same core or another core. Even if there's only your process, the timer still interrupts it. The process may continue on the same core immediately if no other tasks are runnable. Jiffy still increments on each tick. User space is not aware from the Use space process perspective, it's executing continuously, but in reality, it's being interrupted very briefly each tick. Interrupt handling happens in kernel mode. Interrupt handling, sorry, happens in kernel mode. Invisible to your process unless you inspect perf events or use tools like strace. Ooh, what is strace-c? Counter. And strace C. What do you do -c? Oops. Something about forks, follow forks. Alright, summary only. Counts time, calls, and errors for each system call. It puts summary on the program, suppressing the regular output. It shows system time. That's pretty cool. Let's just try that. So we're running strace on openat, and we're gonna do -c, and we're gonna do man to, we'll just say open. Okay. We'll just delete all these, do all that. So it's spending most of its time waiting. That's pretty cool. I like that strace, because you can very quickly see, like, okay, where is it spending its time? That's pretty cool. Yeah, we did 120 calls to new FS stat. OpenAd had 47 calls. This is pretty cool. I gotta tell my friends about this strace-c. Post this on my group chat. Can I do that on a running program? Probably. Okay, I'm gonna do that on a running program. So I'm gonna do, hey, while true, do sleep 1, cat out, Etsy, what do we got here? Something. What should I cat out? Locale. Let's do group. The group file is fine. I'm just gonna pipe it to dev and all anyways. And then done. We'll just do that in a loop forever. And then we'll do psaux grep for bash. And we got 2 bash processes here. Actually, while I'm doing that, do echo, actually no, I'm gonna say echo $. So we got 464.188, 18, yeah, this one here. Oops. strace-c-p maybe? Man strace pid -p pid, yeah, okay. -p that sudo, because I'm gangsta. Oops, I don't want an extra exclamation point there. Please go away. Stop it. Nope. And then if I hit Control C here, Control C, D. Let's do that again. Grab this new PID. and I want to just capture it for a brief time. I can just control C it. So cool. That is so cool. So helpful. All right. Huh. Okay. Okie dokie. Alright, we're reading this AI stuff. The interruption is extremely short, a few hundred nanoseconds to a few microseconds on modern CPUs. So yes, the timer interrupt preempts your running code, increments jiffies, and then returns control. Modern CPUs and tickless kernels, a nuance for modern systems with tickless no HZ kernels. If a CPU is fully idle, the timer interrupt may not fire at fixed intervals. Instead, the kernel schedules the timer for when it's needed. The kernel schedules the timer for when it's needed. But if the CPU is busy, the timer still fires as usual. So your heavy CPU-bound math loop still gets interrupted to update jiffies. TLDR mental model jiffies is incremented by timer interrupt. The CPU pauses user space code briefly to handle interrupts. Interrupt handler runs in kernel mode, increments jiffies, handles timers, maybe triggers a scheduled check. User space resumes immediately afterwards. Even a CPU-bound system called free process cannot avoid being interrupted by timer interrupts. Okay. Why is it that jiffies count such a large granularity? Other syscalls can retrieve much higher granularity of time. Is potentially coarse grain. Tick counter is granularly. Okay. Okay, that makes sense. Okay. Process time is the amount of CPU time used by process since it was created. For recording purposes, the kernel separates CPU time into the following two components: user CPU time, the amount of time spent executing in user mode, sometimes referred to as virtual time. This is time that it appears to the program that it has access to the CPU. System CPU time is the amount of time spent executing in kernel mode. This is the time that the kernel spends executing system calls or performing other tasks on behalf of the program, e.g. servicing page faults. Sometimes we refer to process time as the total CPU time consumed by the process. When we run a program from the shell, we can use the time command to obtain both process time values as well as real time required to run the program. So real is wall clock, user is your use space code, system is kernel code. The time system call receives process time information, returning it in the structure pointed to by buff times buff. The TMS structure pointed to by buff has the following form: user system, CU time, user CPU time of all waited for children. Okay, so children. Okay, the first two fields of the TMS structure will return the user and system components of the CPU time used so far by the calling process. The last two fields return information about CPU time used by all child processes and that have terminated and for which the parent, i.e. the caller of times, has done a wait system call. The clock T data type used to type the four fields of the TMS structure is an integer type that measures the time in units called clock ticks. Okay, clock T data type used to type the four fields, integer type that measures the time in clock ticks. We can call sysconf sc clock tick to obtain the number of clock ticks per second, and then divide clock T value by this number to convert into seconds. We describe sysconf so-and-so on most Linux hardware architecture. Sysconf so-and-so returns the number 100. This corresponds to the kernel constant user hz. However, user hg can be defined with a value other than 100 on a few architectures such as Alpha, Intel Architecture 64. On success, times returns the elapsed real time in clock ticks since some arbitrary point in the past. Sus53 delivery does not specify at what point this is, merely stating that it will be constant during the lifetime of the calling process. Therefore, the only portable use of this return value is to measure elapsed time in execution of the process by calculating the difference between the value returned by pairs of times calls. However, even for this use, the return value of times is unreliable since it can overflow the range of clock T, at which point the value would cycle to start again at 0. i.e. the later times call could return a number that is lower than earlier times call. The reliable way to measure the passage elapsed time is to use get time of day. On Linux, we can specify buff as null. In this case, times simply returns a function result. However, this is not portable. The use of null or buff is not specified in Sus53, and many other Unix implementations require a non-null value for this argument. The clock function provides a simpler interface for retrieving process time. It returns a single value that measures the total, i.e. user plus system CPU time by the calling process. The value returned by clock is measured in units of clocks per second. So we must divide this by this value to arrive at the number of seconds of CPU time used by the process. Clocks per second is fixed to 1 million by POSIX 1, regardless of the resolution of the underlying software clock. The accuracy of clock is nevertheless limited to the resolution of the software clock. All right, although The clock T return type of clock is the same data type that is used in times called. The units of measurement employed by these two interfaces are different. This is a result of historically conflicting definitions of clock T and POSIX1 and the C programming language standard. Even though clocks per second is fixed at 1 million, SUSV3 notes that this constant could be an integer variable on non-XSI conformant systems, so that we can't portably treat it as compile time constant, i.e. we can't use it in if-def preprocessor expansion, because it may be defined as a long integer, i.e. we always cast this constant to long so that we can portably print it with printf. SUSV3 states that the clock should return the processor time used by the process. This is open to different interpretations. On some Unix implementations, the time returned by clock includes the CPU time used by all weighted for children. On Linux, it does not. Example program on Listing 10.5 demonstrates the use of functions described in this section. The display process times function prints the message supplied by the caller and then uses clock and times to retrieve the display process times. The main program makes an initial call to display process times and then executes a loop that consumes some CPU time by repeatedly calling getPID or getppid before again calling display process times once more to see how much CPU time has been consumed within a loop. When we use this program to call getppid 10 million times, this is what we see. Process time, so get. Okay. Cool. Summary. Real time corresponds to everyday definition of time. When real time is measured from some standard point, we refer to it as calendar time. By contrast with elapsed time, which is measured from some point, usually the start in the life of a process. Process time is the amount of CPU time used by process and is divided into user and system components. Various system calls enable us to get and set the system clock value, i.e. calendar time, as measured in seconds since epoch, and a range of library functions allows conversion between calendar time and other time formats, including broken down time and human readable character strings. Describing such conversions took us into a discussion of locales and internationalization. Using and displaying times and dates is an important part of many applications and will make frequent use of functions described in this chapter and later parts of this book. We also say a little more about the measurement of time in chapter 23. Further information and details on how Linux kernel measures time can be found at Love 2010. An extensive discussion of time zones and internationalization can be found in the GNU-C library manual. The SUSV3 documents also cover locales in detail. Exercise. Assume a system where a value returned by the call sysconf SC clock tick is 100. Assuming that clock T value returned by times is assigned 32-bit integer, how long will it take before this value cycles so that it restarts at 0? Perform some calculations. The same calculation for clocks per second value returned by clock. Okay. Alright, kill this, and then we're going to say man sysconf underscore sc clock tick. The number of clock ticks per second. So if it was 1, it'd be 1 per second. 2 would be 500 millisecond granularity, so on and so forth. The corresponding variable was obsolete. It was, of course, called clock tick. Is there sysconf man syscon? Is this 3 GNU clib? Okay. Is there man 2 sysconf? No. How do I check the value of sysconf of underscore sc? What is this? Sc clk tck from the shell without writing. Get conf. There we go. Okay. Assume a system where the value returned by so-and-so is 100, which it is. Assuming that the clock t value returned by times is assigned 32-bit integer. How long will it take before this value cycles? So that restarts at 0. So we say man 2 times. Time stores current process times in the struct. Okay, these are in clock ticks. Okay, well, we'll take the amount, the max. So assigned 32-bit integer and 2's complement would have because you're not going negative, so it'd be 0 and then 1 1 1, that's 4, 0x, one, that's 1 byte, 2 bytes, 3 bytes, 4 bytes. That's a lot. But it's 32-bit. So it'd be 1 bit shift over 1 would be, oops, 2. If you bit shift it over by 31. Two's complement calc. So say we have 32-bit. $647. Yeah, it's gonna be -1. Yeah. And then that times 100. So that's how many ticks we have times 100. Because we have 100 no, sorry. That's gonna be how many ticks. So you have to divide it by 100 to see how many seconds. And then we divide that by 60 seconds, that's how many minutes. Divided by 60, that's how many hours. Divided by 24, that's how many days. So I'm going to say vim exercises.txt. This is going to be 10-1. Can't open file for writing? What are you talking about? Okay. Oh, because I'm in locale somehow. Okay. Let's jump back over to chapter 10. Vim exercises. Paste that in there. Bam. Alright, let's check the answer key. Chapter 10, the maximum 32-bit integer value is exactly... Wait a minute. Yeah, right here. This one here. So it's 2,147, 483, 647 divided by 100. Clock ticks per second. This corresponds to a number 248 days. Yeah. And then perform the same calculation for clocks per second value. Man clock. Where does it say? Perform the same calculation for clocks per second value returned by clock. So that's how many days. If we're at 1 million, then millisecond, decicentile, milli, microsecond. We're not in days anymore. We're not even in hours. 35 minutes. Okay, go back over here. 36 minutes and 47 seconds. Close enough. Why is it 36 minutes? It's at 30, yeah. Is that right? It doesn't seem. It seems like it's a minute off. Let's check his errata. Let's go the Linux program interface errata. And then this would be in the answer key, I think. It should be page 1427. Signed. Huh. How's that 36? So if we do, let me just take this expression again here. Python. Oops. Yank, please. So if we go here and we say, I gotta get ready for my appointment. That's correct. Divided by 100, so we're gonna divide by a million. Should be how many seconds? And then divided by 60. $35, and if I do mod 60, 47, it's 35. I think this might be an off by 1 error here. Anyways, I'm not going to worry about it here. I just don't understand how it's 36 instead of 35. The math just doesn't math out. So I'd like an explanation of what that means, but let's go ahead and get at all, and then we're gonna go over here to readme. I'll mark time as done, and then chapter 11, oops, is going to be system limits and options. Okie dokie, so park it there, get at all, get to C. That needs to be updated. Vim chapter 10 dot clang. Oops, clang. This needs to be chapter 10 here. Build VM. That looks good. All this is the same. And that's his programs. Mine. Stat. Finish chapter 10. Bam. Oops. Let me switch over here. Actually, you know what I'm going to do? I'm just going to end this stream here. I'll go ahead and commit this, push it. I have an appointment in a couple minutes here I need to go to. And then I'll be back this evening after I eat dinner to start on the next chapter 11. But actually, before I do that, we'll just see where I'm at here. on my progress. If I do TN, yeah. T7 and 8 are now done. So it means I am 15% complete. So I'm making progress here. How many pages? I'm 210 pages done out of some like 1,300. Let's see, almost 1,400. Yeah, so I'm making progress. Cool. All right, I'll be back later this evening to start on chapter 11. Cool. See ya.